Department of Physics, Sri Bhuvanendra College, Karkala, welcoming you all to the international webinar, Advanced Functional Materials via Chemical Vapor Deposition, Process, Development and Application, organized by the Department of Physics. The whole world is affected by the pandemic COVID-19. For the detection and prevention of the virus of nanometer in size, scientists were striving very hard by making use of all possible scientific global devices. During this research period, we find it relevant to arrange this webinar on advanced functional materials. For this webinar, we have the resource person, an eminent scholar, Dr. Anjana Devi, Professor of Inorganic Material Chemistry, Ruhr University, Bochum, Germany. I welcome you, Madam, wholeheartedly. Dr. Manjunath A. Kotian, Principal of the College, is supporting and inspiring all the activities of the department. I welcome you, sir.
Thank you, ma'am. Thank you.
I also welcome Mrs. Suvarnalata Shenai, co-convener of this webinar. Welcome you, madam.
Thank you.
I welcome Mr. Divyaksha Prabhu, technical coordinator for this webinar. It's my immense pleasure to welcome all the participants to this webinar. A hearty welcome to you all. Now it's my privilege to introduce today's resource person, Dr. Anjana Devi. Dr. Anjana Devi graduated from St. Agnes College, Mangalore, got her MSc in Material Science from Mangalore University with first rank and gold medal in 1991, completed her PhD from Indian Institute of Science, Bangalore, postdoctoral fellowship from AVH Foundation, Germany, handled habitation project at Ruhr University, Bochum, served as junior professor in inorganic material chemistry, Ruhr University from 2002 to 2011. From 2011 onwards, holding the position of professor in the same department. During the career, Dr. Anjana involved in several professional activities. To name a few, co-organizer of 15th European Conference on Chemical Vapor Deposition, symposiums on plasma chemistry, EMRS Conference 2013. As a project coordinator from 2009 to 2017 of Marie Curie Initial Training Network. She was in the management committee of European Research in Atomic Layer Deposition as representative of Germany. Co-editor of Proceedings of Electrochemical Society in 2005. Member of Nano Center Center of Excellence. Member of Principal Investigator and Board Member of Material Research Department, Interfacial Systems Chemistry, Plasmas with Complex Interactions, Ruhr University, Advisory Council Member of Tentum Lab of Rubion, Member of International Advisory Board of Atomic Layer Deposition and Euro CVD, Member of Electrochemical Society, Materials Research Society, American Chemical Society, and European Material Research Society. Advisory board member of the journal Advanced Materials Interfaces since 2016. Reviewer of about top 30 journals, including Nature Communication. Awards. Professor Anjana Devi got the Research Award from the Rector of Ruhr University at 2002. Best Invention Prize in 2005. Nominated as member of Global Young Faculty and elected as Speaker of the Climate Group of Global Young Faculty in 2009. Recently, in 2020, she was awarded Honorary Doctorate in Technology from Aalto University, Finland. Professor Anjana Devi has 200 publications and 2 patents to her credit. 17 students were awarded PhD under her able guidance. At present, she is guiding 9 students for PhD. She is a visiting professor to IIT Hyderabad and IIT Bombay and Indian Institute of Science. Dr. Anjana has ranked as one of the top atomic layer deposition researchers in the field of precursor chemistry. With this brief introduction, it's my honor to welcome Professor Anjana Devi.
Thank you, Vijaya.
Thank you. Now I request Dr. Manjunath Ekotian, chairperson of the webinar, to give the opening remarks. Over you to sir.
Good morning, ladies and gentlemen. Honorable President of the Governing Council, C.A. Shivanand Pai, Honorable Trustees, respected resource person for today's webinar, Dr. Anjana Devi, Coordinator of the webinar, Madam Vijay Kumari, technical team members, dear participants. At the outset, I welcome you all to this international webinar. Ladies and gentlemen, Sri Bhuvanendra College has built its reputation as a premier institute of learning with diligence and hard work. This year, we are celebrating Diamond Jubilee Year of the college. As a part of celebrations, we have holding a series of webinars. I congratulate the Department of Physics for organizing this international webinar. Ladies and gentlemen, being a teacher of commerce, I should acknowledge that I don't know much about the topic. But today, no domain of knowledge is completely exclusive to any particular subject. It is evident from the title of the webinar, how it is related to physics, material science, and also chemistry speaks volumes about how every aspect in science is interrelated and complex. I have heard that functional materials are a fast growing set of advanced materials and composites with properties that are responsive to external stimuli like light and temperature. Chemical vapor deposition, CVD, is a vacuum deposition method used to produce high quality, high performance solid materials. Ladies and gentlemen, due to the emergence of nanoscience, Professor Vijay Kumar has rightly said, due to emergence of nanotechnology, this process has a tremendous practical implications. Therefore, the topic of webinar is very valuable in terms of its applicability. I strongly believe that deliberations of today will be very useful to everyone interested in science and technology. I'm very much pleased to learn that Dr. Anjana Devi, a professor of international reputation, is the resource person for today. Madam, as head of the institution, I welcome you once again, and I'm sure it will be a very fruitful session today. With all my best wishes, I would like to hand over the session back to Professor Vijay Kumari for further deliberations. Welcoming once again all the participants, resource persons, trustees, and all my friends. Thank you.
Thank you, sir.
Thank you, sir. Now I request the resource person, Professor Anjana Devi, to give the talk. Over you to madam.
So, thank you, Dr. Kotian. Thank you, Principal. Thank you, Vijaya. First of all, I'm overwhelmed by this warm introduction. It's early morning in Germany, so it woke me up. And I'm happy to be a part of this webinar. It was a surprise that I was asked to give a presentation today. And thank Vijaya, because I'm happy being very close to Karkala. I've been a frequent visitor to this place, and it's a pleasure for me to present a part of my research activities that I've been doing in my research group for the past few years. So am I audible, Vijaya?
Audible.
Okay, good, very good. And I just shared the screen. I put in the presentation mode.
Yeah.
Are you able to see it?
Yes.
Very good, wonderful. So, good morning, everybody. Once again, welcome to you all. And I think the audience are from different sectors, so I made my presentation a bit general in the beginning. I would introduce the topic and then go into some details regarding the research details that I've been carrying out in my research group over the last decade or so. So as our principal said, I will be focusing mainly on materials development using chemical vapor deposition, a process that is now well integrated in the technological processes, especially for semiconductors, even other applications too. I will touch upon this very soon. But before I formally move into my talk, I thought, okay, let me just give you an overview. Of course, everybody knows where Germany is, but just to give an idea how big and what are the some specific details. So we have a population about 83 million. And when you see the size of this country, it's about the same area like state of Rajasthan. So you see, it's not very big, but on the other hand, quite densely populated. And you see, we are like, at least Germany is bordered by several countries, and these are all, most of them are Schengen states. And that's one good advantage, that we can cross borders, and this makes actually the European Union very strong, because then you have mobility as well as collaborate. This is especially important for researchers, because you see the young generation of students also coming from Asia. They are able to freely move here, collaborate with different research institutions, and that makes it something unique in the European Union. And you see, of course, this country is involving many different religions. The most of them are from the Protestant and Catholics, but you see there are also other religions, people from different backgrounds. So we have a federal republic here, it's in the government, and Berlin being the capital after the reunification of 1990. And the president is Mr. Steinmeier, and the chancellor is Dr. Merkel. I'm happy to say that she's a physicist. Actually, she did a PhD in physics, and then later on, actually she's a physical chemist, but then did a PhD in this area. And where is University of Bochum? So Bochum is a small place. So this is a map of Germany. You see, perhaps some of you are aware that before the reunification of Germany, Bonn was the capital of West Germany, and we are about 80 kilometers away from Bonn. So this is a small place. Actually, this university was not existing before, but after the Second World War, the government initiated, especially for people from the middle class, because they wanted to send the children for higher education. There was no real university in this area, and this is why this university was built around 1965. So, and you see, the Bochum is a small place. It has about 360,000 inhabitants, and the name Ruhr comes from the river, which I will show in the next slide. And our university is comprising of around 20 faculties. We have about 43,000 students, and also about 5,000 employees. So this is aerial view of our university. And these are the different faculties, the buildings you see here. And right behind, you can see this river, and that's the Ruhr. This university is named after the river. And this is just to show you all that it's a very compact university, of course, from different disciplines, including the medical faculty, and very strong in the engineering and as well as in the social sciences. So, with this background, just to introduce my research group. So I had the team where I have a group of PhD students and a couple of master students, and they are all basically, most of them are studied in Bochum, and then they are continuing their research. So in my presentation today, I will give a brief introduction why materials are relevant for what applications. Of course, I will not be able to cover the complete spectrum, but I will just highlight a couple of cases. And then the main topic will be the gas phase synthesis of advanced materials, why this is important and why it's so relevant, especially in the current technological sectors. And as our principal already said, this is a multidisciplinary field. So there's some background chemistry involved, because you have to have a chemical compound that will be used to transform into a material. And before we do any thin film deposition or deposit any advanced materials, then one has to develop the suitable precursor chemistry. I will just briefly touch this topic. On the other hand, the main focus will be how to develop a process for different functional materials and characterize them. I will take some special case studies, for example, some metal oxides, especially for sensing, which we all know it's a very important area for research as well as in industry, because everywhere, be it pollution or even for detection of some gases, so sensors play an important role. And then there's another material class, or at least two of them, aluminum oxide and zinc oxide. This will be I'll be touching as a gas barrier layer. I will come into the details later why these are relevant. And finally, there's a lot of interest in having materials such as metals as electrode materials, especially to have them transparent. So this is why there's a lot of research being done. Of course, metals are grown using different methods, but you have to make it very transparent and very thin. And this is where vapor deposition processes are much more relevant. And finally, I will summarize my talk. So what's the background motivation to do this research? I mean, all of us are witnessing the miniaturization of devices. Our gadgets are getting smaller and smaller. Of course, they are getting more effective. And this comes to the point, how can we make a device very efficient? And in this way, what are the contributions from physics, chemistry, engineering? Of course, you need the suitable materials and also how you fabricate them. So here are some examples. For example, in the case of micro and nano electronics, you can think of diffusion barriers, the displays on our TVs or on mobile phones, or for example, to connect different devices or some components in the devices, for example, metal interconnects, or in the future, we'll all experience, for example, even our mobile phones may be rolled up and put in the pocket, unlike now a hard case. So in this case, flexible electronics is the future. Or we can think of certain tools, for example, cutting devices or for cutting tools for devices. So in that case, you have to coat the material with certain hard coatings to make them resistant towards wear and tear. So hard coatings are one of the important materials classes, for example, aluminum oxide, silicon carbide, or for example, LEDs. I mean, we witness these days, be it in automobile or lighting in the room. So there are very powerful LEDs. And the advent of new materials, that has been the cornerstone for such new developments. So with this background, and just another important aspect is we are all fascinated by the digital world, right? Every one of us are using some gadgets in some form or the other. And behind this, there are some materials, especially the technology has developed so fast over the last 2 decades that we may not even think about what is inside, So it's just not the hard case outside or the display, but also the electronic parts. And every segment of this device is actually sort of related to the materials that are being used. So, for example, if you think of TV and then you have it just not the screen, you have the LCD display to filter the colors, to get a very good resolution of the images. So all these sectors are actually dominated by different materials. So I would like to give a very sort of general slide as an example. In the past, we all have witnessed, of course, in our master's or bachelor courses, we have soldered some stuff like, for example, resistors or capacitors. And that time they were all bulk systems. So we could see that, for example, you make a transistor or a resistor, you can solder them together. But nowadays, when you open up a laptop or a computer, you cannot see these units by a naked eye. You see some chips. And this is where the miniaturization has taken the upper hand. So one is the miniaturization, the other one is nanostructuring, and this makes things smaller, also efficient, but it's also a challenge. How can you think of having millions of small microelectronic devices on a chip? So this is the beauty of it, that the physicists, the engineers, the chemists join together and strive towards excellence to bring forward the new technology. So I give you another very, very general example. So in the past, for example, if you think of a transistor, here's a schematic. So here you can see the semiconductor, which is silicon. Then you have the polysilicon, which is a metal gate, and in between you have a dielectric. This material, so you have a source and the drain. This is a schematic of a metal oxide semiconductor field effect transistor. So you can see the source and the drain. So in between you have the dielectric material, which is actually storing the charges. And this is exactly what we have in our mobiles, phones, or in our computers. And what was done in the past is silicon dioxide was effectively used as a material to store charges, okay, in simple words. So you can see here is a table, we have the material, and this is an intrinsic property of the material called the dielectric constant. So when you see the values, SiO2, silicon dioxide, has a value of 3.9. So what happened is, as the device dimensions became smaller and smaller, of course, the shrinkage of devices, at certain limits, SiO2 will not be able to store the charges because it gets thinner and thinner. Every part of this device gets smaller. So there will be a limit reached and SiO2 has a big breakdown. So this is why the research was focused on looking for new materials where you can think of a material system called as high K, that means material with higher dielectric constant, which can store more charges, although it is thin. And there are some examples here, for example, hafnium oxide or yttrium oxide or yttria stabilized zirconia. And here you can see the K value, the dielectric constant, it's higher than silicon dioxide. So the use of silicon dioxide for several decades, I mean, this was actually established for many, many years. And so in the early 1990s or late 1990s, they realized, okay, this material will not be able to withstand with the pressure, or at least with the demands for the miniaturization. So this is why we have to look for new materials. And then the research was focused on looking for the second generation of materials that can serve as dielectric oxides, and that deals with the hafnium and zirconium oxides, basically belonging to the group 4. In this case, Gordon Moore, one of the co-founder of Intel, he had predicted that if at all this material SiO2 is going to be replaced by another material, it can be considered as a grand challenge of semiconductor industry. And actually that became true. So in 2007, Intel and IBM announced jointly that for the technology at that time, in 2000, early 2000 or mid 2000s, they found that these materials are actually, they have replaced SiO2. Now the current trend is look for materials which have higher dielectric constants. It's just not the value of the dielectric constant, but they have to be compatible with silicon, with the gate, with the source, because there are new materials also being investigated as a top metal contact. For example, here you have polysilicon. This has been replaced by tantalum nitride or hafnium nitride. And this is where the challenge is that it should be compatible. The materials properties should be also sort of relevant. And of course, the device should function much more effectively. And Gordon Moore, actually, he predicted that, as I said, I just quote him, the implementation of high K and metal materials, that is the tantalum nitride or some other metals, marks the biggest change in transistor technology since the introduction of polysilicon gate metal oxide semiconductor transistors in the late 1960s. And this is the benefit we are all reaping at the moment, because this material has made its mark, is the hafnium oxide, and currently hafnium silicate is the material that is being used as a dielectric material in our gadgets, as a storage medium. So now, it's just not the material, as I said, devices are shrinking, so you need to have deposition methods where you can bring a thin film onto a substrate, and in this case, vapor deposition techniques like chemical vapor deposition or atomic layer deposition, these are the two technologies that are being used in the semiconductor industry, especially because these two methods can help us in coating very large areas. I mean, it can be for 300 millimeter wafers or more. And the advantages, for example, if you see as an overview, I've given a slide here. There are different types of techniques for growing thin films. This includes physical vapor deposition called PVD. So basically you transport the material, physically you transport it, for example, atoms, and then deposit on a substrate, and then you form a thin film. So here's a structured substrate, I would say, and the vapors are condensed on the substrate material and you form a thin film. Now, what is the difference when you go to chemical vapor deposition? Unlike in PVD, here some chemistry is involved. That means you have certain molecules called precursors. They are actually transported in the gas phase. These precursors are then reacted on the substrate surface. They can either go decomposition, In that case, it's called as chemical vapor deposition. So you see a hot substrate. The molecules here, these blue little dots are the precursor molecules. Basically, it's a chemical compound. For example, it can be hafnium chloride for hafnium oxide. And then you can decompose them in the presence of oxygen, and you can grow hafnium oxide films. This is the method to grow hafnium oxide via CVD. Then later on, another variation of CVD, and that's called atomic layer deposition. As the name indicates, here you can actually grow thin films layer by layer at atomic thickness control. So very precise thickness control. And this is actually the method that is being used by Intel or IBM to grow this very thin materials for such applications. So how does it work? So you can think of having a substrate. So here you see on the left side with CVD that you have a molecule or a precursor that decomposes on a hot substrate. The byproducts that are liberated due to the decomposition, basically the organic part, and they are released and pumped out, and only the inorganic material is deposited. Okay. Unlike CVD, in ALD, you also have precursors, but you don't mix the precursors. You use the surface properties, basically a chemisorption of the precursor on a surface that will interact, and you have an exchange reaction taking place. I will show in my next slide how exactly it works. And then you have a sort of a pulse and purge process where you pulse one precursor, adsorb on the surface, allow it to react with the functional groups. And this I can show you better in the next slide. So here you see, you have a substrate. Then you can think of hafnium chloride as a precursor. Then you see the hafnium metal center and 4-chlorine attached to that. So if you have a substrate, normally you have a oxygen or a hydroxyl terminate surface. So when this hafnium chloride interacts with the substrate surface, it will react with the chlorine and the hydrogen, and HCl is released, and then the molecule gets bonded to the oxygen here. Now you have one pulse of the hafnium chloride precursor. Now when it completely occupies all the available sites, then you have some excess, and that is purged. So at some stage you pulse and then purge, and you have a mono layer of the precursor chemisorbed on the substrate surface. Now you want to make hafnium oxide, for example. So you take the hafnium chloride precursor. So then as the oxygen source, you can use water as a co-reactant. So in the next step, once this adsorption is finished here, you introduce water. So this blue little molecule here, that will react with the two other chlorines here. And again, HCl is released, and you have a hafnium oxygen bond formed. And in this way, the excess precursor again is purged out, and you have a monolayer of hafnium oxide formed. So in the last step here, you see hafnium oxide formed, and this actually you can sort of repeat cycle by cycle. You can increase the number of cycles. In this way, you can control the thickness. And the difference when compared to CVD is that you see in CVD, you have a substrate surface. Imagine you want to grow silicon, which is one of the workhorse of the semiconductor industry or the material. And in this case, you have silane as a precursor, which will decompose at high temperatures, maybe 600,000, and form silicon, and hydrogen is released as a byproduct. So you have a thin film of silicon. Now here it decomposes. So basically CVD is a continuous process. The thickness of the layers is controlled by the precursor flux and time. Sometimes you do thermal CVD, so you go to high temperatures. In case you want to grow films at lower temperatures, then you can introduce another parameter, that's plasma, that can bring down the temperature of deposition drastically. So it's called as plasma enhanced CVD. The advantage of CVD compared to physical vapor deposition techniques like sputtering or evaporation or pulse laser deposition or molecular beam epitaxy is that in CVD you can grow very, very large area substrates. And moreover, you can conformally cover it. So suppose you have very complicated geometries, you can actually coat it very uniformly, even very precisely too. And the deposition rate is pretty high, and you can have some complex heterostructures. So that means you can have different materials stacked one over the other. So here is a sort of a cross section of a substrate, and the film formed, that's hafnium oxide, just to show that the TMP image shows the nice demarcation between the substrate and the film. Now, in the case of atomic layer deposition, as I said, it's a pulse and purge process, so it's a discontinuous process, unlike in the case of CVD. So here, because of this discontinuous process, you can actually have a very precise thickness control. Again, as in the case of CVD, you have a very large area of homogeneity, very dense layers, and also conformal coverage. Most importantly, you can grow the films at very low temperatures. This is an advantage. I will show you with an example later on why ALD is taking the upper hand these days, especially when you go into, in the future, for example, flexible electronics, or coating your plastic bottles or pharmaceutical products where you want to protect it from outside atmosphere. Then you need to coat with some materials that will prevent some oxygen or water transmitting inside. So this can be done at low temperature, and this is why ALD is much more relevant than CVD. Now, one particular feature of ALD is, as I said, thickness control. So imagine you pulse the precursor and purge it into the next precursor, purge it, and you have a thin film form. It can be activated or one cycle. So imagine when all the sides are covered, then the growth saturates. That means that you attain a state where no more growth is possible. Then you repeat the cycle. This is where then you can see for every cycle, you can actually increase the number of cycles and increase the thickness. And then you have a linear dependence. So for example, 10 cycles, I have 10 nanometers, 100 cycles, I have 100 nanometers. So this is where you can precisely control the thickness. And when you have a precursor, which is actually a molecule that is brought in the gas phase, you may have to make sure this precursor doesn't decompose. Otherwise, you may end up in a CVD process. So you have something called the ALD window, where the precursor efficiently reacts with the co-reactant and forms thin film. And this is a range we actually operate at. So first you have to optimize the process, look at the temperature range where you actually get a saturated growth, and also you can linearly control the thickness. And this is where we work on, especially the ALD window. So these are the typical characteristics that are very relevant. And you see here, if you see a trench, for example, how nicely one can coat the film on a trench substrate, or you can also see the nice interface, or very clear demarcated interface between the film and the substrate. So we are talking about nanometer thick layers, couple of nanometers, 1, 2, 5, or not more than 50, 100 nanometers. Then you go to the CVD range, okay? So the main principle is you have a chemisorption and a sequential self-terminating reactions. That's what I said, pulse and purge. And this is where you can have a very good thickness control. And also you see, when you have high aspect ratios, that means the height to the width of the structures, then you can actually uniformly grow, also conformally grow. And this is where in the microelectronics, where you have very deep trenches, this is where ALD is taking, sort of playing a pivotal role. So there are different materials that have been tried or also implemented in the industry to a certain extent with CVD or ALD. So it can be metals, semi-metals, carbides, sulfides, nitrides, phosphides, selenides. So it spans the entire periodic table, different combinations. And the role of material scientists is to see whether we can develop new materials with new functionalities that can be advantages for certain applications. And in this case, the main parameter for this CVD or ALD process is a precursor. So as a chemist, one can say, okay, I make some molecules in the lab, and a material scientist would then say, I will test it in the reactor, whether it works for CVD or ALD. But before that, one has to see whether this molecule we buy or we synthesize in the lab, they should be volatile. That means you should bring it in the gas phase without decomposing. So it can be aluminum trichloride. This can be commercially bought, or you can think of trimethyl aluminum. This also is a very pyrophoric compound, but also can be commercially bought. They are very volatile. Then they should be reactive to the substrate surface as well as to the co-reactant. In ideal case, the precursor should be volatile. For CVD, it should have a temperature window. That means you should not decompose very low at low temperatures, neither at very high temperatures. So you should have a safe operating window. Then, of course, it should be stable. It should cleanly decompose. For commercial application, it should be cheap to buy or synthesize. It should be, for safety issues, it should be non-toxic, non-explosive. And particularly for atomic layer deposition, you need to have a precursor that is reactive, because as I said, it's a self-terminating reaction with the exchange of the different groups, and thermal stability, because if thermal stability is a weak point, then you may end up in a CVD contribution. So the role of a chemist is to develop new molecules, go away from the classical precursors because there are certain drawbacks with them. And we researchers look into such details where we can think of having different ligands, combination of ligands, be it nitrogen coordinated, oxygen coordinated, or just the halogen coordinated ligands, and see if we can improve upon the existing class of precursors. So my research group, actually the main focus is transforming molecules to materials. So look for inorganic molecules, organic molecules, transform them to materials using CVD or ALD. And recently we have also sort of gone into molecular layer deposition. That is something to do with the organic molecules, similar to atomic layer deposition, where you basically have inorganic materials. Here you can think of molecular layer deposition, coating organic coatings on substrates, or also the cheapest method is where you have no vacuum, is solution deposition, where you use dip coating or spin coating to deposit films. So we do the deposition. First of all, we synthesize the precursors, we deposit the films using different techniques, and then characterize them in detail in terms of structure, morphology, composition, using a complement. And we cannot do everything, so we collaborate with engineers on campus as well as with national and international collaborators who test them for devices. So the materials of interest are several. That depends on the projects that we are sort of handling at the moment. And our approach is to tackle the current challenges in materials development. What you do is basically you try to nanostructure the materials or different functional materials at the atomic scale, whether we can reduce the thickness, also the functionality can be modified. So basically you modulate the properties and then test it for different device applications. And this is where the material synthesis has a main focus, and that is actually the title of my talk, where you see either your CVD, ALD, or MLD, or chemical solution deposition, using the same precursors that we synthesize for different technological sectors. So the infrastructure we have in the department, my group, that we, of course, these compounds are mostly air sensitive. They can be pyrophoric, toxic. So we normally use glove box. Also, you can sort of avoid air or moisture. Then we characterize them with different analytical tools. You see NMR, mass spec, UV visible spectroscopy, single crystal X-ray diffraction, and also looking at thermal properties, because it's one of the important figure of merits for characterizing a precursor. And when we deposit the films, then we analyze in terms of structure, X-ray diffraction, microscopy, for example, the morphology, the topology, looking into the interface, looking into the optical properties, composition, photoluminescence spectroscopy, or atom tomography. This is one of the new techniques to look into the composition as well as the distribution of the atoms in a material system, and also Raman spectroscopy for characterizing the films. So the infrastructure in terms of film deposition, you see that in the slide, we have some self-built CVD reactors where the students themselves assemble and they test the precursor. So the minute we have a precursor which is having good thermal properties, we test them in test reactors, and later on we sort of transfer to the commercial systems that we have. This is for the nitrides, this is for the oxides, and this is all the CVD reactors, and these three beneath are the ALD reactors. It could be the thermal ALD, it could be the plasma ALD, and this is one of the small reactors we recently built. It's thermal, but basically for molecular layer deposition for organic coatings. So the projects, as I said, they are funded by different agencies, and you see it depends on the area. For example, it could be microelectronics, where you see we grow the dielectric oxides, or channel materials in the case of thin film transistors, or metal electrodes. Currently we are working on silver. In today's talk, I will touch upon a couple of materials, for example, aluminum oxide as gas barriers, or silver as top electrode materials, tin oxide for gas sensors. So there are different projects, and also we are now getting more into energy-based material, for example, supercapacitors for storage or for catalysis or water splitting, for example, photoanodes or photoelectrochemistry. So you see there are a multitude of material systems, and this can be used for different applications. So what is the main motivation? As I said, we want to make new materials or improved materials using CVD and ALD, and the basic parameters of precursor. So you may ask me, why do you want to make this precursor? Actually, there are several precursors known and they're commercially available, but each of them have pros and cons. So what we do is basically we assess the drawback of the existing precursors, because some of the precursors are not really good. You just take it from the cupboard and then you try it, but it may not work. On the other hand, if we want to get over the drawbacks, then we have to do a systematic engineering of the molecular chemistry, and that is one part of our research. So we look for different ligand systems, we modify the precursors, see whether we can influence the volatility, stability, reactivity based on the intramolecular and intermolecular interactions within the molecule, or also change the reactivity, tailor the surface chemistry, or use alternative co-reactants. Sometimes to make oxides, the molecule may not react with just water or oxygen. Then you have to go to ozone, very harsh medium, but nevertheless, that's only means to get a good reactivity. So in that case, what we do is, so this is a schematic where I can show you. This is the ALD principle, what I mentioned before, where we have the pulse and purge. Then you have a reactor where you introduce this molecule here in this channel here. So this is a precursor molecule. You see, you have metal and a ligand surrounding it. And this molecule is then transformed to form a material. So here is a TM picture of a silicon substrate, and the gadolinium precursor, what is here, it's reacted with water and it forms the gadolinium oxide layer here. And this is a transmission electron microscopy image. And here you can see the X-ray diffraction to show that the films are polycrystalline, and they are actually of a thickness of 10 to 20 nanometers, not much. And together with the engineers, we make the transistor structures where you see, for example, here's an example where we grew hafnium oxide on silicon, and then you have platinum silicide as a top metal electrode. And this transistor structure was sort of built together with the engineers. And here you see the aluminum top contact, then you have the dielectric, the hafnium oxide, and aluminum is a top metal. So basically we have capacitor structures grown using the ALD process, and then they are tested for example, you look into the dielectric constant, you look into the leakage current. These are some of the issues that the engineers investigate and see whether our process that we have developed is actually relevant for some application. So here's one example which is a very common material system, aluminum oxide, that you all have experienced. So we know aluminum oxide, it can exist in as bulk, and it has very good mechanical properties. It's a ceramic, it's biocompatible, and also very resistant to temperature and chemicals, and a wear resistance. This is something very important. So they can be used as protective layers, for example, in tools or automotive applications or aerospace, especially in the airplane. So you have a very thick coating of aluminum oxide, which can withstand extreme conditions, especially when the flight takes off. You have a change in pressure, temperature. So all this material is very relevant for that. Then it also has very good refractive index and good transparency, so it can be used for optical applications, for example, solar cells as anti-reflection coatings, or in the case of aluminum oxide as such, because it's a very dense material, so it has very high density, and when you have a very dense material, then the seepage of water, oxygen, or moisture through the this layer is minimum. So that's the reason it's used as the gas barrier layers. That means you do not let any outside atmosphere to seep through into a device. So especially in LED TVs or our displays, you see that the whole LEDs are sort of packed by gas barrier layer. That means you coat a very thin layer of aluminum oxide. Currently, SiO2 is actually in the market, where they grow ALD. Or ALD grown SiO2 is actually in the market, that is used as a gas barrier layer. And the conditions are that the material must be thin, it should be transparent, and it should also prevent any diffusion of gases from the outside. Or you can think of aluminum oxide for electrical applications. It has a very high band gap and also a good dielectric constant. So it can also be used as a dielectric layer in TFTs. So when you want to have very thin layers, and I said in the past, or in the earlier slide, that you have very good thickness control, good uniformity, conformality at very low temperatures, and this is where ALD is the method of choice. So we can actually give an example why we need this method and why this material is of interest. So imagine you can have a Coke bottle. It's basically a PET bottle, right? Polyethylene terephthalate. So there's one parameter that's called as the OTR, oxygen transmission rate. So this can be used as a benchmark. So if you have an OTR that has a unit of cubic centimeters per square meter per day. So for a Coke bottle, I mean, of course, it's a degradable product, our Coke inside. It can also degrade over a period of time. On the other hand, we have to make sure that no oxygen or water gets transmitted inside or seeps through and degrade the Coke inside. So normally you have plastic PET and then a very thin layer of SiO2 coated on it. Okay, so to prevent the diffusion of the gases from outside. So this value 10 to the power minus 1 to 10 to the power 1 is not of high end. But when you go to more exclusive applications, for example, pharmaceutical products, I mean, we don't want our medicine to degrade because of moisture. So especially in a country like India, where we have very humid conditions, then it's important that we have a very good protective layer. Or even for electronic applications, for example, here solar cells, So here you would like to have a material that has very good barrier properties. So you see the demand is still higher, minus 3 to 10 to the minus 1. When you go much advanced applications, for example, in electronics, in flexible electronics or OLEDs, then you have that the range from minus 6 to minus 4. This is quite demanding, I would say. So now it's not only the material, it's not only the OTR value, but also how can you coat at low temperature, because all of the packaging material are plastics. They will not be able to withstand temperatures above 100 to 150. For example, polypropylene maybe not beyond 80. PET also maybe less than 100 degrees centigrade. So this is where ALD is the method of choice, because you can actually grow films even at room temperature as long as the precursor is reactive. And here you see there are many materials that can be used as barriers, for example, aluminum oxide, SiO2, TiO2, zirconium oxide, or you can use a combination. So if you take your PET bottle, your Coke bottle, actually it is actually you have a polyethylene terephthalate, and then you have a thick layer of maybe 100 nanometers SiO2, which is done by CVD, plasma enhanced CVD. It serves the purpose because it's a fast method, it's cheaper compared to ALD. ALD is a very slow process, but very effective. On the other hand, for cost efficiency, you also need a process where you can make it cheaper. And PECVD has been well established for decades now to coat this, for example, Coke bottles or the pharmaceutical covering materials. In that case, you have a coating of SiOX. And when you actually look into the PECVD coatings, through a microscope, you can actually see there are some defects. Basically, there are pores. So I call it defects. This is a porous film. It may not be full of pores, but certain pores may exist because the coating time is pretty fast. So actually, this defects, these pores can deteriorate the OTR, because through these pores, oxygen or water can diffuse through and basically affect the inside material. So in that case, you need to have avoid the pores, and ALD would be the method of choice, because you can have very dense coatings, actually pinhole free films, and you can get very good OTR values. So if you see, for example, a standard approach would be, okay, take a PET substrate and then coat CVD SiO2 and protect the underlying PET bottle or your substrate. On the other hand, you can think of having a very thin layer of ALD of maybe 1 or 2 nanometers, and then you're making sure that this underneath substrate is completely free of any pores, or at least there's no seepage, and then you have the PECVD coating. The other option is that you have a PECVD coating like this, and on that you cap it, okay? So these are different approaches one can see, seeding and capping routes, where you can effectively block these pores and make sure the OTR values of at the high end. So when you want to grow aluminum oxide, so as I said, in the precursor chemistry plays an important role. Commercially available precursors for aluminum, for example, trimethyl aluminum, It's a very volatile compound. If you open the bottle, it will burn in air. It's highly pyrophoric. It has a very good reactivity, very good for ALD. But the issue is that it's hazardous, as I said, and also because of at low temperatures of deposition, the carbon moieties are present in the ligand. They can also get into the film, which can affect the functional properties. So people have tried to modify the precursor. For example, here you see you have two methyl groups, like here you have three. So one of the methyl groups is replaced by an alkoxide group, that's an oxygen coordinated ligand. And in this case, you sort of reduce the reactivity. On the other hand, this is good because it's not so pyrophoric, but still carbon incorporation has been an issue. So you have made some compromise on the reactivity. On the other hand, it still works as a good ALD precursor. So our goal was to look for new ligands that will actually totally make us free from the pyrophoric nature. So we try to hunt for ligands. I mean, we don't have to look for totally new ligands. You can, I mean, there's a lot of organic chemistry done for ages. So in the past, the group of Schumann, he just reported one ligand called the DMP. That's a dimethyl aminopropyl. That means the dimethyl amino groups are here. And there actually, he just made it as a synthetic paper. So we looked for certain ligands of this type, varied the different groups here, and thought, okay, by using this chelating, basically coordinating this metal center and making it less reactive, in this case we were able to sort of develop a compound, and this was known but not as a CVD or ALD precursor, but just out of interest for inorganic synthetic chemistry. So my student Lucas, he actually was the first one to initiate this. So he said, okay, let's try this DMP ligand, whether we can develop some precursors that are not pyrophoric, and can it be a substitute for trimethyl aluminium. This will be a big breakthrough, because then the industry will be very happy, because they can make large quantities. You don't have any special means to store it, like as for TMA, you need to be extra careful in handling. So we synthesize the precursor. I will not go into the chemistry details, but just to show that we are very much involved in synthetic chemistry. So we make the precursor molecules, look into the structure, chemical structure. You see single X-ray diffraction shows the metal atom, the surrounding ligands, and we use different synthetic routes and see the NMR, whether the molecule is formed, the spectroscopic purity, and most important is the thermal properties, as I said in the beginning, whether the precursor will volatilize or evaporate or sublime as a function of temperature. Because in a CVD process or ALD process, you have to bring it in the gas phase. So here you can see a graph where you have the weight of the precursor measured as a function of temperature. So you have to take a precursor in a small crucible, heat it. So after certain temperature, you see the weight loss occurs. That means the precursor is losing weight, and it continues till high temperature. At certain temperatures, there's nothing left in the crucible. This is a good sign, showing that the precursor can be evaporated, undecomposed, and it's exactly what we need in a CVD and ALD process, because you have a bottle where the precursor is stored, you heat it and bring it to the gas phase to the reactor. At the deposition zone, it should react, not before. So that means from this graph, we can actually see that the precursor sublimes or evaporates without any decomposition, which is a good sign. That is the first important parameter, apart from the purity, that we have to investigate. Then in this case, we try to the usage of this precursor, this aluminium DMP precursor, both for thermal and plasma. So the goal was to see whether this precursor just reacts with water to form aluminium oxide, and if we can use plasma to bring down the temperature where we can coat polypropylene or polyethylene terephthalate. So this was the main aim, and we developed a process with water as well as with the plasma. And here you can see, maybe you can recall the first slide where I showed the linearity, that means the thickness as a function of number of pulses, or also you can see there's the ALD window where you have a broad range where you can operate as a function of temperature. So you measure the thickness or the growth per cycle as a function of temperature, and then also the saturation. So after some eight pulses of a precursor, the growth saturates. Then you introduce a new precursor, and then it continues. So we can also change the precursor pulse, the water pulse. So these parameters can be varied, and then you get a film. And from the X-ray reflectivity, from the fringes here, you can calculate the thickness. Then from the atomic force microscopy, here you see it is a film, for example, around a couple of maybe 10, 15 nanometers. And then you have the root mean square roughness is around 0.39 nanometers, which is actually pretty low comparable to that of a underlying silicon substrate. So you have a film of around 20 nanometers here or 30 nanometers here. So this shows that the ALD process is successful both with water as well as with plasma, and that is the advantage because you can actually try it for plastic substrates as well as for silicon substrates. Now the goal of the project was to see if we can test them for gas barriers. So here I can show you the oxygen transmission rate as a function of thickness. So you see I grew the film of different thicknesses, 2.55 or 20 nanometers, and then I measure the OTR. So if you see the OTR in the beginning, basically it's very high, that means it's not good. That means the films of thickness less than 5 nanometers has a very poor OTR value. So lower the value, the better it is. So now as you see, as you increase the thickness of the film, the OTR drops. That means around 5 nanometers, you are able to get good OTR values. And in the case of the other precursor, we compared two precursors here with a similar ligand system, but varied the combinations. And I have some certain terminologies which you don't have to know about, because it's just a fancy name. But when you had the two precursors, we saw that, okay, the precursor 3 had OTR minimum around 5 nanometers. After that, it saturates and slightly increases. On the other hand, with the other precursor, the DMAT precursor, you see even at higher thicknesses, still it decreases further and then increases. This increased thickness is also not good because, or increased value is not good because it could be that there's some stress and strain involved when the thickness increases, and then the film can sort of rupture, or there could be some grain boundaries through which the water can or oxygen can diffuse. So this is a range where we would like to operate, where you have the very good OTR value. So if I compare the OTR, take for example the bare PET plastic foil, okay? So you have 80 cubic centimeter per square meter per day. Now if I quote, for example, 5 nanometers of aluminum oxide from this precursor, then I bring down the value from 80 to 3. Now if I increase the thickness to 15 nanometers, I bring it down further. So now you see, basically you have an improvement factor more than 90%. And that's quite a sort of impressive result, because you're able to tune the OTR values based on thickness, and with such small thickness, for example, 5 nanometers, nothing, right? So we also try to make a combination, just not by aluminum oxide. So here you can see the SiO2, which is actually now in the present day technology, it's used very effectively for as gas barrier layers. So then we tried, let's see whether we can make only aluminum oxide. The OTR was not optimal, like in the case of SiO2. Then we also had some different thicknesses and also combinations, you see. Finally found that the value of 5 nanometer aluminum oxide and 5 nanometer silicon oxide, that was the actually the optimal combination to get a very good OTR performance, So the bottom line is that the precursors has a very important influence, and the film thickness has a second influence, and one can optimize this, okay? So this is one example of the barrier performance. So we want to sort of summarize in this case that the precursors, we do a lot of precursor chemistry, test them for CVD or ALD, and in this particular case, we had a non-pyrophoric precursor, which is quite sort of relevant, as I said, because you would like to have or minimize all the safety issues. And this also in terms of cost, it's an advantage. And we think that we assume that the DMP-based precursors, actually, they can compete very well with the commercially available precursor. So this was published last year or so in Chemistry European Journal. And then the next example, I want to show you the sensors, because something this all of us are actually sort of actively involved in. So we know that, as I said, be it air pollution or be it detection, for example, also in biosensors, also in stents. So these are the this is a sector which is developing very fast. And when you see this chart here, you see there are several metal oxides, be it zinc oxide, titanium oxide, tungsten oxide, tin oxide. They're all N-type semiconductors having certain band gaps. It's an oxygen containing material. And there are also p-type semiconductors. There are quite only few of them, which is copper oxide or nickel oxide. And this just shows the statistic number of articles coming up, in this area. It's just sort of booming. And these materials have different band gaps. The highlight of this material is that they have always this oxygen deficient surfaces, and that is quite interesting for gas sensing, because you can basically sensor, a solid gas sensor is based on the gasochromic effect. So you have adsorption of molecules, the resistance could change. So when you have, when you expose a material, for example, in one of the oxides here, the resistance will decrease upon exposure to reductive gases, or the resistance can increase when exposed to oxidative gases. And this is where you select the materials of choice and for which gas sensing. And this is where, again, we would like to grow these materials. They are available as bulk. The standard sensors are bulk or thin films. But when you want to have large areas, thin materials with better functionalities, then maybe CVD or ALD could be a choice. So just to give a background on tin oxide, it has the cassiterite type structure. So you have the tin as the green balls here and oxygen as the red ones. So here you see the packing here, and actually this material has certain oxygen deficient surface, and this is where the conductivity can vary depending upon the presence or absence of the adsorbed species. So you can absorb certain gases, and when you sort of measure the resistivity as a function of time and you pulse a gas, then you can see these variations. Okay, so typically for this material, you can use it for chemical sensing, for example, ammonia or H2S or hydrogen or CO. That is one of the outgassing materials in automobiles, in our cars or so. So this is where it's getting more and more relevant. And not only for sensing, because it is they can be transparent. They have a band gap of 3.6 eV. This also makes them interesting for thin film transistor applications as channel materials. So transparent conducting oxides is another upcoming field where one can implement them in TFT applications. So the important thing is how we can modulate the properties, the surface properties, by depositing these materials which are basically oxygen deficient, and then how we can actually employ them for sensing or for in the case of TFT applications as a channel material. So I will sort of just briefly summarize this slide. So there are several precursors. You can have the alkyls, the chlorides, or the iodides, but most of them have certain drawbacks. The only commercially available precursor is tin amide here with the nitrogen coordination. These are research sort of oriented publications where it's not commercially available. There are certain pros and cons, but the most important precursor is the amide here, and they have high volatility but limited thermal stability, and that's not good for ALD. Then the non-commercially available precursors, as I said, they may not be optimal, but people have tried, and that's the goal of the researchers, to look for new molecules, new processes. So what was our aim? To look for alternative tin precursors for low temperature. So my doctoral student, David, he actually looked into this aspect where he used the same ligand, the DMP ligand, what I mentioned for you all in the case of aluminium. So he tried to make a tin precursor and looked into the purity in terms of NMR, mass spec, elemental analysis, and then looked in the thermal properties. Here you see a beautiful TG pattern, a thermal analysis pattern where weight loss is a function of time, and the precursor sublimes and with absolutely no rest mass, so that means it's cleanly volatilizing, and also vapor pressure. It is determined, that means what is the optimal pressure in the reactor at a certain temperature. So all these characterization tools, or at least the techniques that we use, renders this precursor actually very appealing both for CVD and ALD. And that's what we did. So we went ahead and tested first for CVD. So we used this precursor in combination with oxygen and check what happens. So when you look at the graph here, the X-ray diffraction pattern here, the films were amorphous or at low temperature, and as the temperature increases, they grew more crystalline, and that has been sort of also confirmed from the scanning electron microscopy images. So you see at low temperatures, you have sort of agglomerate structures. As the temperature increases, the grain size increases, and then you have some sort of structured growth. And this actually, this very high surface area. It's very interesting for sensing applications. And when we look at the atomic force microscopy images, you see the roughness of the surface on the silicon substrate around 10.2 nanometers. This is pretty high. Maybe you recall when I told aluminum oxide it was around 0.3 nanometers. That is good for gas barrier applications where you want a very smooth surface, no holes, no grain boundaries, nothing. Absolutely amorphous film. Here you want a crystalline material with high surface area because for sensing applications, this is more relevant. So this is just to show you an example where surface roughness is much higher. Of course, the temperature is much higher. This is a CVD grown film, not ALD, but you see around 800 degrees, you can have intertwined elongated grains, which could be interesting for sensing applications. It was not only for CVD, but we also tried for ALD. So this is the ALD reactor we use. So this is the holder where you have the substrate. And once again, we tried ALD, and at low temperatures, we were able to grow tin oxide films. Here you see, from this graph, you can see the growth rate as a function of temperature. We're able to grow films at temperature as low as 60 degrees centigrade and as high as 220 degrees centigrade. Okay, and then we investigated the saturation, the linearity. It all showed typical ALD characteristics. And important is that we found that at such thin layers, you have a very good interface between the substrate and the film. It is also confirmed from the TEM analysis. Also, the required phase is formed. And what was also sort of in the beginning confusing, why we are getting high growth rate at such low temperature? Was it condensation or is it a real film? But we checked, and later on we saw that during the composition analysis. So we use X-ray photoelectron spectroscopy to look into the composition at different temperatures. 600 and 150 were the two temperatures, as I showed in the slide before. Here you have 60 degrees here and higher temperatures, so around 150 was optimal. And then we looked into the composition. So there you see at you can measure the X-ray photoelectron spectra, and as deposited as well as usual, you know, when you have a film, the outer surface is basically sort of contaminated with the hydrocarbon from the outside atmosphere. So you sputter the first couple of mono layers or first nanometer layers, and then you look into the bulk of the film. And here you see be 60 degrees or 160 degrees centigrade, you can see that the films contain species, not only tin oxide, but also some hydroxide species. Okay, it is reduced at high temperature, but still there's some contribution. And this is a very good sign to show that it's not only SNO species, but also SNOH species that is inside the film. And that can also be one of the reasons that we may not have a perfect stoichiometry. You can see the carbon is very low on the outer surface. Before sputtering, you see around 17 atomic percent, but after sputtering, that means you remove the first couple of layers, and then you see it's coming to less than 0.2 atomic percent, which shows that the film is actually very pure. And the oxygen deficiency, as I said, this is one of the advantages for sensing applications. So you also, in the low temperature, you also have the monoxide. This is a dioxide, and you have the monoxide, but high temperature, this species from the monoxide disappears here. So the spectra is deconvoluted, and you have the different species here. And in that case, you can actually assign the OH species and the SNO2 phase here. But here you have a small contribution from the monoxide. Again, we looked at the AFM, and you see the roughness is pretty low. In the previous slide, the CVD, I showed you all that the roughness is around 10 nanometers, but here you have less than 0.2 nanometers, which is actually a good sign that the film is very smooth, dense, and we get very conformal coverage. Now, finally, the application was to see, okay, can this film be used for TFTs as a channel material? So the engineers, they actually made a structure of a TFT structure where you have the N-type, heavily doped N-type silicon, then you have a thermally grown oxide, and then you have the electrodes, top electrodes, and then on that we actually, before that we coated the tin oxide by ALD. That's the process we use at 60 degrees centigrade, and measured the IV curve. So you have the source and the drain current with the gate and source voltage here, and then you measure the saturation here and the transfer characteristics, and for the films of different thickness. we found that for the film of 6 nanometers, we had an optimal electrical characteristics in terms of mobility, which is around 12 centimeters square per volt per second, which is quite impressive when you compare it to the literature values known for ALD grown films. And of course, the on-off ratio, this is very important because for switching applications, right, this will be very good, and we have around 10 to the power 7. And we have to keep in mind, all these are as deposit films. There was no annealing done after the deposition. That means the as deposit films are actually stoichiometric and also functional. So this is to summarize the electrical properties. And the same ligand, once more, Lucas, during his PhD, he tried it for zinc, which is zinc oxide is also a very cheap material and very interesting for different applications. And here also we used the similar ligand and made zinc precursor. And what we saw is that the films are smooth. They're actually at very low thick. Actually, you see the temperature, when you see the deposition temperature, maybe for example, 60 degrees or 140 degrees centigrade, they're crystalline at such low temperature, nanocrystalline, I would say, not highly crystalline, which is sort of normal because ALD is a low temperature process, and the ALD characteristics were confirmed. But what we found is that you can increase the crystallinity as a function of temperature, and you see the thickness varied from 10, 12 nanometers to 50 nanometers. That was the range we optimized this process, and the films were smooth with the very low roughness. And the first thing was, okay, zinc oxide has several applications, or it can find several applications. Transparent conducting oxide. So that's one thing is, okay, can we look into the optical band gap? So we did some UV visible spectroscopy. You can see the absorption as a function of wavelength. So this is the tau plot where you can, from the absorption curve, that we can calculate the band gap. So for films for 50 nanometers, between 480 nanometers, 800 nanometers, we had a very high transparency. So I can, 1 minute. Yeah, it had a very high transparency. In the case of the optical band gap, it was around 3.26 that we estimated, which is sort of agreeing with the literature known values. And then the other application we went is, okay, what about the gas barrier? Because this is also an interesting material. We found that for a film around 7.5 nanometers, we had a good OTR. Above that, it increases. That is because, maybe you can recall, as the deposition temperature increases, the crystallinity increases. That means there are pores or there are grain boundaries, and that is why the water or the oxygen function of thickness. Then we also try to, or the engineers try to see whether we can build up some TFT structures with zinc oxide channel material. And again, the transfer characteristics, for example, the IV characteristics was measured, and you see in this case, the threshold voltage around 16 volts here, as well as the field effect mobility was around 0.2 centimeters squared per volt second. So this material, as in the case of aluminum oxide, has several functionalities as gas barriers, as transparent conducting oxides, and also from the UV, we see that they are highly transparent. So the final application was, okay, sensing, because that was one of the main project goals. And we found that this particular material system that we grew at different temperatures has show some sensing activities for different gases. And particularly for NO2, we found that they have higher sensitivity. And here you see, you can actually measure the resistance as a function of time. So you pulse the gases, and then you see whether the resistance increases or decreases. And as I said, we checked for 2 different temperatures. And here we see the NO2, CO, and ammonia were the mixture of gases that were introduced. And when you measure the sensitivity as a function of concentration of, for example, in particular case with NO2, we found that the films grown at low temperature were less sensitive compared to the films grown at higher temperatures. This is because the crystallinity increases, and as I said, it's an oxygen deficient surface. The number of oxygen species, be it OH, O, O2 minus, all of them are higher at higher temperatures compared to low temperatures, and this is why the sensitivity is higher. So you can see, just by tuning the temperature, you can actually activate the surface. And in this case, as I said, we checked as a function of temperature with different gases, and we found that for the oxidative gas, especially for NO2, that the concentration of level was 0.06 to 1.5 ppm, and it shows the typical N-type semiconducting behavior. So there was no cross sensitivity. There is also an important aspect, because sometimes you cannot differentiate between different gases. And when we compared this to a commercially available sensor, we found that the sensor temperature was around 300 degrees centigrade. This material system actually was operating quite well, or in fact a little bit superior compared to a standard solid state sensor that is used in for such applications. So that was the conclusion of this part. So just to show that actually chemistry plays an important role, where you see that transforming molecules to materials, be it for OTR, be it for TFT, or be it for sensing. We just published this last month in Small, where we could show the full chain, starting from precursor chemistry to thin film deposition and different applications. And one last final example, just I need a couple of minutes to wind up this my presentation. So we are always talking about miniaturization, and I only gave examples for oxides. It can be nitrides, sulfides. They are all emerging fields, and sulfides especially. 2D materials, people are talking about 1D, 2D, and 2D materials are also taking the upper hand. And there's a lot to explore. There's a lot much more to explore in this area, but that's not the topic I'm touching. But I want to just highlight one particular example: metals. And metals, actually, one may think, okay, you just evaporate a metal and then it's formed, which is true, which is normally done. But then when you think about solar cells, okay, so when you have a device with so many stacked layers, for example, you have the glass on the top, the indium tin oxide, the top electrode, So this is a transparent layer, the glass. Then you have the top electrode, that's the indium tin oxide. So there are several organic layers in between in the solar cell. Now, ITO, indium tin oxide, is a material that is normally used, but indium is getting extinct, so it's very expensive. So one has to think of other electrodes, and now the option comes, okay, why don't we just take a metal, because it is a conducting material, right? But then metals are not transparent. They are actually opaque. They are highly conducting, but they are not transparent. So for such application, you need transparent conducting electrodes. Or, for example, when you think of in an integrated circuit where interconnects are copper interconnects are used, so you need very thin layers, and in this case, ALD would be a matter of ALD is a deposition of choice, and copper is a very good material system as an interconnect. On the other hand, there are no processes for copper, or at least very well established in terms of ALD. So people have normally used this the Deposition process, and they use ultra thin conformal copper, for example 10 nanometers, and on high aspect ratios you need to have really conformal films that are continuous. And when you see, copper is a very good material, but I said the tendency with metals is that when you have a substrate, for example, you know that the growth on different substrates of metal films, it's different. It can be island formation, then they can join, percolate, and form a continuous film. But then at some stage, the films become thicker, and then they are opaque. So I would like to have a film that is very thin, and then you nucleate such that you have a monolayer, and then you can have very thin layers, which at the end can be transparent as well as conducting. And that is a challenge, because the mechanism that is known for deposition of during the deposition of metal layers, it's actually dictated by Vollmer-Weber island growth. That means you have certain islands formed, they join together, and then you have a percolation. That means you have a continuous film, but you end up in thicker layers which is not transparent but maybe conducting. But now you want to have thinner coatings which are transparent and conducting. And that's the challenge. You're talking about 10 nanometers. So copper has been always a headache. Silver is a good choice. It is expensive. On the other hand, it has a good high melting point. It has a low resistivity, and also actually you can grow them, but still this issue will come in terms of percolation and higher thickness. So for solar cells, for example, you need transparent materials, conductive materials, and one possibility is to replace this ITO with silver. Same stack of material system, but instead of ITO, you could take silver. So now, what is the challenge for the industry or for the researchers? Whether we can grow silver by ALD. So far, if you look into the literature, there is only one precursor available for ALD or CVD of silver that is working. I mean, it's a working precursor. There may be several silver precursors, but whether it is working for ALD effectively or CVD, we don't know. But then it was shown that this precursor, it's commercially available and you can buy it and use it. But if you closely look at the molecule, you have silver, you have phosphor, you have phosphorus, you have oxygen, you have fluorine. All these are actually detrimental for film growth because first of all, you don't need phosphorus and fluorine. They can be a poison in the film if they come as impurities. You don't want any silver oxide forming because of the oxygen here. So one would like to go away from these different elements. So, but this is the only precursor working. Actually, this is a workhorse of this in the case of metal ALD, but there was no other choice. So what we were thinking is, why not get out or get away from this phosphorus or fluorine? So we tried to look for different ligand combinations. So you see, you have silver, you're coordinating through nitrogen, not through oxygen. Then we have silicon, which is a sort of stabilizing this metal center here, and this chelating ligand, for example, the carbon. So I say this as a NHC, that is the heterocyclic carbon, and this I call as hexadimethylcellulamide, that is the HMDS ligand. Okay, so we synthesized, we made it was a complex procedure in the beginning, but later on we optimized it. At the end, we got a very nice molecule. So you have a linear molecule, silver, which the HMDS, that is the hexamethyl diacethylamide, and the NHC here. And this compound was isolated. And what we did was also try to see how different it is from this precursor, or at least what are the characteristics. So Nils, the doctoral student, he investigated this project, and then he found a linear molecule. So you see a single crystal extra diffraction of one crystal of the silver precursor. You have silver here, then you have the HMDS ligand, so silicon is here, and then you have the carbon-based ligand here, and a linear molecule. And we found that this molecule is actually forming in high purity. We could confirm the molecular weight with mass spectrometry, and the thermal properties. You see weight loss as a function of temperature. It could be volatilized. It melts at around 100 degrees, and we can bring it in the gas phase, undecomposed, and that was actually quite interesting for application for ALD. So we didn't stop at that stage. So together with the collaboration partners in Wuppertal, close to Bochum, they have a spatial ALD at atmospheric pressure. I was always talking about ALD and PALD, but not spatial ALD. One drawback with ALD in general compared to CVD or other methods, it's very slow process. I mean, you need maybe hours to get a couple of nanometers. So for example, 30 nanometer film will be grown only in 6 hours or so. And for example, in the case of aluminum oxide. So this is a very slow process. On the other hand, the development is so good that to increase the efficiency, people have now devised a reactor where you keep the reactor fixed. Normally you pulse and purge, right? But in this case, you have several feed-throughs, so you move the substrate, okay? So in this case, the efficiency is higher, and then you can grow thicker films in a shorter period of time. So they have, our partners, research partners, they have this setup, and Wuppertal, and what they did was we gave them both the precursors, the commercially available, that's here, and with the one we made. They tested it under similar conditions, same substrate, same temperature, same flow rate, using the dielectric discharge plasma, which is a mixture of hydrogen and argon, and then they varied the temperature from the vaporizer, from the substrate. It's around 100 degrees centigrade. Again, you see it's a very low temperature. And then we found that surface coverage. So you see with this precursor, you see some sort of grains. They're not well connected. And if you look at the from the SCM, the surface coverage is around 62% area coverage. And when we looked into the new precursor, we had higher coverage, okay? And the growth rate, it was enhanced. So you have 0.14 angstrom per cycle. And in this case, you had 0.36 angstrom per cycle. So we found that the precursor with this non-oxygen, non-fluorine, and non-phosphorus has a better coverage at lower thickness. You have well-connected layers, and then the resistivity was of the order of 10 to the minus ohm centimeter after 1,800 cycles. So this was one of the, I would say, a big success for our group, because that was the first report where we could show that you can have very thin layers of silver which are conducting, and one can come down further with the thickness to make it more transparent. And that's an ongoing research where we're looking for molecules or process parameters where we can scale it down further. So with this, I will conclude my presentation. I hope I could convince you all that ALD and CVD methods are both are very technologically relevant for depositing advanced functional materials. They are well established in the microelectronics and easily compatible with the photolithography as well as electrode formation, all that, the main criteria is that you need to have suitable precursors for both processes. And as I said, it can be used for large area growth, which is important for scale up. Especially ALD can be also used effectively for very smooth films, very homogeneous layers, but it is slow. But new variants are growing. For example, as I said to you all, spatial ALD is one of example, or roll-to-roll ALD. Basically, you have batch reactors where you can have foils, large areas, meter squared foil, area foils. And just for your information, LG is the company which makes our TVs. They have already introduced this displays that has been at the moment. PALD with different materials are being actually coated with ALD for the current version of the TV what we buy from LG, and also Samsung recently also opened up. They are also using ALD. This is for high volume manufacturing. I mean, we are not doing such things. We are actually doing it at the very fundamental level where you screen precursors, develop processes, and the emerging technologies that will be interesting for all of us, be it in energy, be it in protection layers, be it in flexible electronics or biomedicals. So it has a bright future. And I think as a chemist, as a physicist, as a material scientist, we have plenty to explore. And with this, I would like to conclude. I cannot stop it without acknowledging my funding agencies. I've been quite lucky getting support from different agencies, be it from the German Science Foundation or from the Federal Ministry or from the European Union, and also the some joint projects with our international partners. And recently we set up, if people are interested in CVD and ALD, we set up a blog. My group has set up a blog where we have launched a Twitter bot where we can follow up on the recent developments on CVD and ALD research areas. And I'd like to thank my group. I have a very nice team who are very, of course, they're young and energetic, so it's fun to work with them. And they have been highly productive, and actually their success is my success too. And finally, I would like to thank the Bhuvanendra College for this invitation. And it was a pleasure to take part in this webinar. And I'm open for questions. And thank you for your kind attention.
Thank you, Dr. Ranjana. Here are a few questions. The first question is, how does, Dr. Ranjana, am I audible?
Yeah, I'm able to hear. Thank you.
How does this gas barrier layers used in OLEDs? Yeah. This is from S. Ghosh.
Okay. So maybe I go to the slide. That will be easy to explain. Yeah, I just take an example of solar cells, okay? But you can think of your OLEDs. For example, you have the substrate, your functional materials, a channel, then you have the organic layers, which is a channel material, and on the top, because this material can be sort of susceptible to outside atmosphere, oxygen or water. So in that case, you need to have a coating of an inorganic material which is dense and doesn't let any gases coming in. And because it's organic, then it's not possible to coat at high temperatures, right? So it will be the process, because you can go up to room temperature to coat aluminum oxide or silicon oxide. And this is, the material is transparent as well as it is protecting the underlying layer.
Okay, thank you, madam. The second question is, can we deposit ZNO layer on the top in gold layer using ALD without changing the property of ZNO?
So can we coat zinc oxide on what? Can you please repeat, ma'am?
Can we deposit ZNO layer on top of thin gold layer?
Gold, okay.
Gold.
Okay, good. So you have to keep in mind, the nucleation of materials on different surfaces varies. So an ideal case, I showed you always OH terminate surface. For example, silicon is normally terminated with OH, then it's easy, the OH will easily sort of cling to the incoming precursor, and then it forms an O and zinc bond, and then it's easy. But when it comes to metals, the nucleation is totally different. So as I showed you all this nucleation issues where it forms islands. So in that case, one may have to try to use some wetting layer, which will actually sort of smoothen the process to form a good interface. Otherwise, you may have some islands which may lead to disconnected films. So we have not done anything on gold, but I know that people have tried on gold substrates by using an intermediate or wetting layer to grow such oxides. In principle, yes, but then, or you can use a plasma treatment. So you can have a hydrogen terminated surface. You can take a gold surface, introduce a hydrogen plasma. Instead of OH termination, you can have a hydrogen terminated surface, and then you can introduce a precursor and then form a zinc oxide layer.
Thank you. One more question. How to minimize the defect density on the film and how to confirm it?
Okay, so you see it's all low temperature process, right? So this pulse and purge process, in the beginning I showed you all that you can pulse the precursor, purge it. So you optimize the pulsing and purging. So this can be actually, we have an in situ mechanism where you can, using quartz crystal microbalance, you can actually see the surface coverage, okay? So you can monitor the film growth as a function of time, and then you get the saturation. But ex situ, in situ we do with quartz crystal microbalance, or ellipsometry, we do quartz crystal microbalance, but ex situ, what you can do is, we can analyze by AFM, you look for pinholes, or SEM, of course, the SEM, because we are talking about a couple of nanometers, that will be a challenge. But AFM and TM are the two methods we normally use to check the coverage of the films.
Thank you, madam. Next question is, can we deposit lead and silver multilayer on ZNO tin film using ALD technique?
First of all, lead. Okay, lead is an interesting material, but lead is actually banned from using anymore in the future. I think it's one of the most toxic materials. There are very few lead precursors, so I think the future for lead is very low. Definitely there's a chance to do it. You should be able to identify a good lead precursor, but there are very few, and especially because of this ban of not using any more lead in the future, this is sort of, the prospects are less. But yes, in principle, yes, it's possible to grow any material, but you should have a suitable precursor.
Madam, same question is continued.
Yeah.
Suppose yes, whether it forms diffuse layer or layer by layer formation.
Okay, the thing is, because the temperature is so low, the formation of the sort of multi-component, ternary systems is less, unless the temperature is very high, where you have sort of an interdiffusion of the layers, but or the surface is very rough, then you have interdiffusion, right? But you talk about ALD temperature around 100 degrees or maybe maximum 150, 200, not beyond. So I think that, as you said, the diffuse layers would be sort of more of an option than have a sort of a composite.
Thank you, madam. One more question. Is it possible to use solution-based processing techniques effectively for the fabrication of transparent conducting electrodes of low-dimensional carbon-based materials such as CNTs or graphene, etc.?
Yeah, right. You know that carbon nanotubes has been explored a lot, yeah? And CVD has been a method for making graphene-based materials. So you know that graphene was invented in like 2010, got the Nobel Prize, and then actually they use a Scotch tape, but later on people say, okay, when you want to scale up, I mean, this is a headache, right? I mean, Scotch tape won't work out. So CVD, you can use methane gas at high temperatures in the presence of a catalyst like copper, and then you can grow thin layers of large areas. But solution deposition, as I said, it will be useful, especially when you want to have low cost, but large areas, it will be a challenge. So the tendency would be to have crystalline materials, because in solution deposition, again, you're having low temperature. So to control the crystallinity will be difficult. You have to do post-deposition annealing. I would prefer directly to go up to a process where it directly gives me crystalline layers with high quality. So then I would go to CVD. ALD will not be an option because it's low temperature, unless you post an inlet.
Thank you, madam. Good afternoon. Myself, Swarnalata Shanai from Department of Physics. Dear participants, we have come to the end of the session. It's my privilege to propose vote of thanks. The resource person of the webinar, Dr. Anjana Devi, Professor of Inorganic Materials Chemistry, Ruhr University, Bochum, Germany, has enlightened and enriched us on the topic Advanced Functional Materials via Chemical Vapor Deposition, Process Development and Application. Madam, the session was very informative and fruitful one. On behalf of management, principal, faculty, and students of Shri Bhuvanendra College, Karkala, I thank you profusely. Thank you, madam.
Thank you.